So today we are restarting our meetup in West LA. And before we start, I have some announcement to make. First, this year is the 10th anniversary of this group. So 10 years ago, Szilard and some other people who love coding in R started this group and started meeting around UCLA regularly. And that's why we have almost 1,900 people in this meetup group, because it's been growing for 10 years. And I would like to celebrate that a little bit today with donuts. and I don't want to take all the donuts home, so please take some donuts after the meetup. And my plan for this group is we're going to have monthly meetings on Westside, usually at the end of month. This is to avoid conflict with the East LA R user group. They usually have meetings at the beginning of the month. And sometimes we might have joint meetings. And yeah, that's the plan for now. And we're looking for speakers, talk about what you do with R, something interesting. Today we're going to talk about machine learning in R. And yeah, anything you do with R, that's fun, you can email me. And we're going to have next meeting on June 27th at Retina AI. And we're still finding a venue for July 31st. And also looking for speakers. And we're constantly looking for venue, so you can email me if you would like to host us. And we're creating a network of our users in SoCal because it's a very big place. And if we want to make R accessible to everyone and everybody can join me, that we have to have local meetings in various areas. And this is why we're creating Slack space, Twitter, GitHub. We're merging everything so you can find all the meetings in the same place. And we're also sharing the email. So if you would like to give a talk and you live in Pasadena, most likely you can give a talk near your home. And Ethan is going to tell us about Philosophie, who's kindly sponsoring us and hosting us today.
Hey guys, so just a quick spiel on it. So first of all, I've been coming to Szilard stuff forever, and so I'm super happy to finally be in a space where I can help host and stuff. About Philosophie, Philosophie is a really cool company to work at. If you think you might want to work here and think you're a good match, you should definitely apply. It's by far the best place I've ever worked. It's a great culture. It's a cross-discipline, essentially a consulting firm, cross-discipline across designers, UI, UX, product managers, really strong engineering, and small teams on on projects from like 2 weeks to 6 to 9 months, and completely different stacks every time, completely different topics, verticals. So if you love like learning new stacks all the time and working on fun projects with fun people, this is a great place to work. If you want to, you can talk to me at any point if you want, or just email like info@Philosophie or something if you're interested, or check out the website.
Okay, so let's welcome Szilard for today's talk.
All right, thanks for having me. So 20 years ago, 25, I was doing physics, and then I moved to finance, and then to California, and to the data science. And I've been running some of the meetups around here, and also the website DataScience.LA. I've been also teaching at 2 universities, one in Europe and UCLA. And I have some machine learning benchmarks, and I'm going to touch a little bit on that in this talk. And of course, this has nothing to do with my employment. So, deep learning, how many of you have seen this slide? Hopefully many. Yeah, at least half. So Andrew Yang has been running around for a while, saying that deep learning beats other machine learning algorithm. And of course, deep learning beats humans, and we hope to have self-driving cars very soon. And then we can rest. We don't have to go to meetups anymore. AI will do everything for us. So the reality, I think it's a bit far away, and then it's more nuanced. So indeed, for images and computer vision, deep learning is great. Also, recurrent networks, LSTMs, are good for sequence modeling, and combined with reinforcement learning, deep learning has had indeed tremendous success in environment where you can create infinite amount of data, so basically games and virtual environments, but not really in practical business applications. So I think the current state of AI is pretty much more like this. And on the other hand, we've been having machine learning in businesses, many applications since at least the 90s, but even in the 80s. So for many, many years in fraud detection, credit scoring, marketing analytics, manufacturing, telecoms, like churn and insurance and all these applications, we've been using machine learning quite successfully in many business and practical applications. And when deep learning became hype, I was also trying to see if deep learning beats some of the most accurate algorithms like random forest gradient boosting. On some of the business data I was working, and some public data that it's kind of similar. So I tried to tweak deep learning and talk to deep learning experts, and then I couldn't really beat the more traditional machine learning algorithms such as random forest or gradient boosting. And then we had Tianqi at the LA Data Science meetup. He's the author of xgboost, one of the most popular boosting library. And he was talking about that more than half of the tables are won with boosting and not really by deep learning. So kind of my answer to Andrew Yang's slide is like this. I think for this kind of problems where you have business data in tabular format, gradient boosting actually beats deep learning in many cases. And then also Anthony was here at the meetup, and later he's been talking about the same thing, that basically most of the taggles that have this kind of tabular data are won by xgboost. So it used to be random forest, and once data got bigger and more complex, then boosting. But this should not be surprising to some of us who have been doing machine learning for a decade. So there is these two papers I like to cite. They are both from 2006, but they're absolutely not outdated. So these guys have looked at, took many algorithms and have tried on many data sets, and we're looking which algorithms are giving the most accuracy. And so these data sets are a bit smaller than in Kaggle, so random forest was kind of like the winner, and then neural networks boosting support vector machines, logistic regression. And even without knowing these papers, I remember in 2007 I did my first machine learning production project, and guess what? That was a random forest in R. But the algorithm is not really the most important thing or the only important thing in a machine learning projects. You have to clean your data, you have to do feature engineering, if you want really top accuracy, like in a tagon, then you want to ensemble many models. And ultimately, you have to do all this process, the workflow of data science or machine learning. You have to explore the data, do visualization. You have to do all this work in order to get a good machine learning model. And actually, so this would be kind of like the algos and the tools, but in fact, there are even more important things than the tools. This is called statistics. So you might do things that are just invalid if you don't know what you're doing. So kind of like if you want to just try something simple on your data, and here's some little guidance of what works pretty well if you don't want to spend a lot of time. So if you have tabular data, then I would try gradient boosting or random forest. If you have very small data, like hundreds of observations, maybe 1,000, then even random forest gradient boosting will overfit. You have to go with something simpler like linear model, logistic regression. If you have a lot of data, then GBMs and random forests become computationally too expensive. You would have to run training for hours or days. So we will usually do, again, some simple model, linear models, usually with stochastic gradient descent on really huge data. And of course, if you have images or speech or some of these other problems where deep learning is the best, then yeah, use deep learning. But a more accurate answer would be it depends on your problem, on your data. Or you can try them all. So there are like 4 or 5 algorithms you want to try, like random forest, gradient boosting, support vector machines, neural nets, and linear models. So you can just try them all. Or you can also tune the parameters for gradient boosting. There are a lot of parameters you can tune. I was also already mentioning that in order to get top accuracy, you want to use ensembles, and it matters a lot how you do the feature engineering, how you incorporate domain knowledge into the modeling. And ultimately, in some projects, the accuracy is not really the most important thing. So sometimes you want more interpretable models because of regulation or because of other reasons, kind of debuggability. So you might want to go with other models. So I think by now you can see that the title, Better Than Deep Learning, was completely misguided. So it depends. On some data, like especially what you find in business, a lot of times gradient boosting is the best. But of course, for images, deep learning is the best. So just know what to use. So let's see a little bit more about GVMs. So GVMs are made of trees. Basically, we are building decision trees and we are averaging them. So these decision trees are this kind of recursive partition of the space. So basically, we split on variables depending on whether it's more or less than some cutoff, some split. And then this is how we get from the data this whole structure in the splits. So here is another example of a tree grown on some data. And before gradient boosting, there was something called tabular. So this is building trees. Each tree is built after we build the previous ones. And then each tree is trying to minimize the error that the other trees have been made. And this is done by equating those observations that the previous trees are misclassified, and then down weighting the other ones. And then at the end, we average these trees. So gradient boosting is very similar. We build sequentially trees, and we're going to average them. And then the way we build it is that we take a step in the direction of the gradient. You don't need to understand this, actually understanding. So you can go to my favorite book, the Friedman, Elements of Statistical Learning, if you want to understand exactly how it's working. But in practice, you have to understand other things. So it's good to know that there are trees. For example, because there are trees, you don't need to scale the inputs. Like, for example, like for neural networks. But otherwise, it doesn't really help to understand the formulas. So what tools to use if you want to use gradient boosting? So I asked myself this a couple of years ago, and I talked to people at meetups who I meet, and also I was reading Kaggle forums and other things on the internet. So these were the packages at that time. So we had our meetups, so our packages, Python, H2, xgboost, Spark MLlib. Actually, xgboost came a little bit later. And why open source? So it's free, but not only because it's free, but to run very nice meetups like this one. If you do a SaaS meetup, probably like 3 people will show up. So open source has really a very cool community. There are conferences like Saturday and more meetups here. Actually, people used to complain about R like 10 to 15 years ago that it had poor documentation. That was kind of a general problem with open source. But I think by now there are way more books on R and with R than with like SAS or any other commercial tool. So actually, I think that now it kind of wins on documentation as well. And ultimately, open source is R or Python. So I'm biased towards R, but I know half of the people are using Python. There is no problem with that. So I was interested in what would work, and I didn't really want to do any work, just Googling. I couldn't find really any kind of benchmark comparing the performance of these tools and how much data they can take and train reasonably and not crash out of memory. So in around 2015, I started this benchmark, which I still call this kind of limited and incomplete. So basically, I was comparing the performance of tools like training time and memory usage and accuracy. And it's on GitHub. You can see scalability graphs like this. And so you can see that there is even 10 and even 100 times difference between running times of different tools, even though you would think that they implement the same algo from the book, but there is huge differences in how good it is. And the best ones are xgboost, H2O, and then later on Microsoft open sourced another tool called lightgbm. So I think these are the 3 best, but you can go to this repo and see more details. And all of these 3 they have like R and Python packages. So these are xgboost and lightgbm are C, C++, and H2O is Java. So basically, if you're running it from R or Python, you're running the same code. What about Spark? So you can see that Spark was pretty slow, and I have some more numbers later. So I think Spark is not really adequate for like data science or machine learning, and it's kind of like it's just too clunky for kind of interactive and this kind of research kind of way of doing data science and exploratory data analysis. But people will tell me that they have big data, or everyone has big data. I would say maybe not everyone. So don't be ashamed if you don't have big data. It's not like I have big hands or something. So, and there are surveys about the size of data people are really using for analytics, and they are far from really big. So big data appears mostly in raw data. Let's say you have clicks of users, but when you want to do analytics, usually you refine and aggregate the data. Let's say you want to do analytics not on clicks but on users, so you create these user features. So you would reduce the size of the data a lot. So by the time you get to modeling machine learning, your data is much smaller. Usually fits in RAM, and RAM is very cheap, so you can get hundreds of gigs into a server or just go on the cloud, any of the three big cloud providers. So this 250 gig instance was available when I started the benchmarks. Then right now there is this 4 terabyte instance available, and if you are like a very good customer, then you get this 12 terabyte instance from Amazon. So it's way more than enough for fitting your data into the RAM of one server. And I also looked back at the surveys about the dataset sizes. It appears that in the last 10 years, they've been growing 20% a year, and RAM has grown by about 50% a year. So actually, the RAM has much faster growth rate, the affordable RAM or some proxy of it. And I think by now, people have realized that actually what they want is kind of fast machine learning, and not to work on big data, because their big data already fits in RAM. And speed matters for many reasons. So it's not that you usually don't just train one model. So you have to do cross-validation. So let's say 5-fold, that's already 6 models. If you do hyperparameter tuning, you might try 10 to 100 models you would have to run. So, and then if you do ensemble again, you would run, I don't know, potentially 100 models, and maybe select 10 of them and sample them. So speed really matters. So you cannot use something that for training one model takes an hour. So, or it will be very expensive, right, if you train it on 100 servers. So from that old benchmark, I kind of transitioned to this new repo, which I focus on GVMs only, and I made it much more reproducible and easier for me to run it. So there is like a Docker file, and so you can just go there and try it on your machine. So it will install everything and download the data and run it. So I ran this a couple of weeks ago, and so lightgbm is the fastest on the CPU. These libraries have now GPU implementations, and GPUs are great also for gradient boosting, so you can parallelize the histogram calculation on it, but you're not going to get the speed up you get in deep learning, like 10x, 10, even 100x, some people are saying. So here you get a little bit of speed up, but it might be worse. So you can see here that xgboost is the fastest GPU implementation, and that for larger data, like the 10 million records, you are faster on the GPU than with the CPU. And then, if I looked also like 100 million records, and I also added this new library called catboost. A lot of people were asking to look at that. So that's another one used commonly by Kaggle and by some people. So unfortunately, it's kind of slow, and also it uses a lot more memory than the other ones. But you can see there is also correlation. So the fastest one also uses the less memory. And memory becomes an issue, like with 100 million or even more records. Actually, it becomes an issue on the GPUs, right? So you can see here that catboost crashes because it doesn't have enough memory to run. So yeah, I will summarize a little bit later, but you can see that if you have a CPU, basically use lightgbm. If you have a GPU, use xgboost. Or if you care about putting your model in production, then I would say, especially if you want to do real-time scoring, then I think H2 is the best. So it is very easy to just download the binary of the model and build a prediction service. They have a separate open source product called Steam. So this is all you need to do to build a web service that, so basically you download the binary, you build this WAR file, and then you run jetting, and then you can score. And it's very fast. It's like a few, 2-3 milliseconds, even for a huge random forest of rainy boosting machines. It's fine. I have a full code here on this list, and I will make the slides available. So ultimately, this is kind of a redraw of the data science workflow. So ultimately, in Kaggle, you do only this top part here, but in practice, it matters how you deploy and you do the scoring, and then you build all this kind of monitoring and online evaluation. So I think H2 helps with this part. So I have some updated numbers on Spark. So it didn't get any better. So you can see that the speed. So this is lightgbm training. This is Spark. So 200x. It also uses like 100 times more memory. So here on so 103 is that, and it crashed even on the 1 terabyte memory server. So I have no idea what it's doing. Well, actually I do. So in comparison, you see that, right? At least 100 times more memory usage. Like lightgbm is using 5 gigabyte RAM. So let's run Spark on a cluster like a real big data person. So of course you need, so what Spark people would tell you need bigger data and you need a cluster. And unfortunately it's so slow that I just didn't have the patience to run it on 103, so I ran 10. On 100 million records, it's running for like half an hour. So you can run it locally on this huge server with a terabyte of RAM, or you can run it on a cluster. It's gonna use 700 gigs. And Meanwhile, lightgbm on like a smaller instance is gonna run for 60 seconds. Gonna use like 5 gigabytes. So you can see for comparing the RAM usage that, and this is like cluster of 10 nodes versus lightgbm on one single server. So you can see that there is a lot of room here to add more data and just run lightgbm on like a bigger memory server if you want. And it's still gonna be way faster than any reasonable size cluster. So I've been playing a little bit around. I put my hands on a like very old laptop, and even on one core, running this on a laptop is faster than Spark on a like 10 node cluster. So yeah, I think it's garbage. Forget about it. And ultimately, I think it's like distributed computing is hard, especially for machine learning. So the state of the art is like tools with less features, slow and buggy. And I think Spark is okay if you use it for ETL. It's not the greatest, but it works. It's pretty good. So people are using it. And if you really want to do machine learning, use something else. Or Spark has now integration with basically with H2O and xgboost. So you can call out from Spark into H2O or xgboost. So I didn't test this extensively, but I tried it out and it kind of works. So for machine learning, ultimately what you want is high performance and the tools that have been designed with high performance computing. And by people who know what CPU caches are, those are the ones that are the best, or right now the GPUs. So one thing I want as a data scientist at least, I want to write as little code as possible and use like a high-level API, and all the top 3 tools, they have very nice high-level APIs. Basically, you read your data, do maybe one until coding, and then you transform it to a format that it's optimized for learning, and then you just pass the hyperparameters, and there's the training and there's the scoring. So GBMs are complicated things. They have a lot of parameters. Here's for H2. And the most important ones are number of trees, depth of the trees, and then learning rate. And then this thing called early stopping. So early stopping is something you really want to do because like neural networks, if you train GBMs too long, they're gonna overfit. So the accuracy on a train set will look like if it's increasing, but on a test set it's starting deteriorating. So early stop will stop here. And all the 3 top GBM implementations, they have early stopping is just like 1 or 2 parameters. There is a lot I could talk about tuning, but I'm losing my voice. And there is also this, for example, this good blog posts. And ultimately, tuning is about finding the right complexity. and optimizing the performance on a test set. If you do tuning, you can do this kind of manual search of try to poke with the hyperparameters. Can do grid search, random search. There is this great paper that shows that random search is much more efficient than grid search. So don't do grid search. Read this paper. So I have a repo by playing around with random search with parameters. A few other things about performance. So I was never a fan of distributed computing, but it turns out that having too many cores also is sometimes not very helpful. So here's the runtime by 1 core, 2 cores, and threads. So you can see that xgboost is becoming faster as you have more cores, as you would expect. But if you have 2-socket CPUs, which now it's pretty common for a lot of high-end servers or even EC2 instances, then it's going to slow down. You put more threads, it's going to slow down even more. Then sometimes it can be like a 20 times slow down. This is because each CPU is linked to its memory bank. So if this one wants to read something from here, it's going to do it over like a very slow bus. And this creates slowdowns. So these tools have obviously not been written with this kind of NOMA awareness in mind. So they're working on this, but also hyper-threading can slow down things. And I noticed this in 2016 and it's still not fixed. So basically my recommendation is to, if you don't use the hyper-threads, did cores, and you can do like different models or cross-validations on different sockets. So just pin it to the corresponding cores. So you would run like, I don't know, in this example, like 3 times faster if you do this versus running one model on all the cores and then the other model on the other cores. Even on physical cores is not the speed up, the scaling is not linear. So you see that on even 10 million records with lightgbm going from 1 to 16 physical cores, you get 5 times speed up. With xgboost 3.5 times speed up. So it's not any near to 16. So I have now a new collaborator, and he's been looking at if you want to run multiple models. For example, in some use cases, you would have to run 100 models every day. What's the optimal way to run it? And it turns out that very unsexily that basically 1 model per core. So that's the optimal way. Because of the sublinear scaling, it turns out that this is the highest throughput. So here's kind of like a summary of what I was talking about. So if you care mostly about speed, training speed, and if you have a CPU, use lightgbm. If you have a GPU, use xgboost. If you care a lot about this kind of real-time scoring, deployability, use H2O. Kind of the same thing. I like to do this kind of polls on Twitter, very informal. So, how many people are using linear models, random forest, GVM, net? So this is obviously biased by my followers. They like to use random forest GVMs, but a lot of people are using them. So, what's the favorite gradient boosting library? So, xgboost got very popular with Kaggle a few years ago before lightgbm existed. So, and here is the other two. How many people are using GPUs? This was a year ago. And this is now. So it starts increasing a little bit. I did a more extensive. So this poll was from a year ago, and in Twitter you cannot have more than 4 options. So I did another one where you could have more options. You can see that it's kind of the same, the top 4. And then catboost are the old GVM package. This is the one I used in 2007. And the other ones. So it seems like by now people figure out which are the top 3 and they're using depending on the use case. Another thing to motivate using of GVMs was the winning solution of the at Kaggle Days a couple of weeks ago. And so basically what they did, they have a blog post about the winning solution, and they did, of course, what I was mentioning. So basically, feature engineering by exploratory data analysis, then using lightgbm, they were using CPU, then created other models with xgboost, logistic regression, and the forest. And then they throw in a neural net here. It wasn't very good, but they ensembled it with the other ones. And that's basically it. So I think probably the takeaway is if you have tabular data, use GVMs. And here there are a lot more repos. And here's my contact. So that's pretty much for now, and we can open it for questions. Thank you. Yeah.
So you said, what if you compare sort of like the ease of use of doing something like deep learning where you don't have to do feature engineering or hyperparameter tuning, if you just go right out of the box with one of those algorithms?
Well, with deep learning, you don't have to do feature engineering for images. But in business use cases, deep learning is not going to figure out the features, so you still have to do feature engineering. And hyperparameter tuning, you have to do it in either case. So I don't think it's easier to use.
For like the H2O application, I didn't know how it works. You download a training library, so you're training it offline, and then you download the libraries.
Yeah. Yeah. Yeah, it's not online learning. Sorry?
It's not downloadable. It can't be downloadable.
Where you refer to online learning, that basically as we go we learn from on the fly, or I don't know what you're referring to. So
Just H2O in particular.
yeah, you can do it on your laptop. So yeah, all the 3 they run on a laptop too. Or so basically you have seen that sometimes one core is enough. If your data fits in the RAM of a laptop, then you can use easily a laptop. Otherwise, you need like a server. Yeah.
Yes, doing it on the laptop. I'm going to xgboost and use a GPU.
Mm.
Yeah, I'm like CPU. So,
Yeah.
what's the best way to go about that? I like the GPU option. Just use my built-in video card.
Yeah, it's so all these tools are easy to install on Linux box. With with Windows, it goes from hard to impossible, and with Mac, kind of the same. But yeah, so if you have a Linux box with some not very exotic GPU, you can just compile it, and it's gonna work. Especially xgboost. So on the GPU, xgboost is not only the fastest, but it's kind of the most stable and mature library, I think. Yes. About the early stopping. So early stopping is very easy. So what early stopping is doing is looking at the metric on. So you have the train set, and you have test set or cross validation. So from the train set, you want to set aside a part for validation, and then it's gonna look at the metric, let's say AUC for binary classification or whatever you specify, and it's gonna see when it's going to decrease, and then all of them, they have different parameters a little bit, but I think xgboost has something like stopping grounds. So it's gonna stop let's say stopping grounds 10 is gonna stop after there is no more improvement for 10 consecutive runs. And then it knows the history, so it's gonna give you the best. So basically what early stopping stops you from, it's not only that you are overfitting, but you could like fit a lot of trees and just look back at the, let's say, performance on a validation set, but then you just train it, you just wait CPU time. Because why train 1,000 trees when the best is at 127, say. And then the parameters so you see for each door is stopping grounds and metric. And this. So the tolerance is how much it's decreasing. And then xgboost is just one stopping ground. And I think you can select the metric too.
How about as far as variance and bias?
Mm-hmm.
Did you notice any difference between different packages?
So I put here accuracy numbers, but so this is just based on one data, so I wouldn't worry too much. So if you pick other data set, is gonna. So this looks more accurate than this one, but for another data set, it might be the other way around. And it's very much dependent on data, so I don't think it's possible to say anything. So people actually even use catboost because sometimes it's more accurate than the other one. So I think some people in catboost, what they do all the four and then they ensemble them. But for production, it's kind of then you have to maintain four.
So, something important is the feature engineering, using these GBM models. Like, I've heard of theories like, if you promote features, developer, you know, if you have put some
So feature engineering is usually more important than the algo. So, and I mean, it's not the number of features, but which features contain the information. So you might get rid of one feature, but if that's very significant, then the whole model will decrease in accuracy. So basically, is you have a problem, and then you have data, and then you have the algo, and the algo doesn't learn from the problem, it learns from the data. So if you add something very important to your data set, you start collecting it, or you add it to the model, that might boost the, or increase the accuracy.
But if you have like no feature, does it work?
No, I mean, so it depends, but yeah, for a low number of features, like a few hundred or 1,000, it doesn't hurt. You might overfit, but so neither of these tools can deal with millions of columns. So if you want millions of columns, then I'm not sure if there is probably no good GBM implementation. People are using linear models, like Opal. Yes.
Wondering, imbalanced data sets, imbalanced classes, did you do any tests between the different implementations of any there's better and others from hyperparameters in these sets?
I did tests between different methods of dealing with imbalanced data sets. So the options are you downsample the majority class, or you upsample the minority, and there are different methods, or you do something in between. So it turns out that for a lot of data, just the simplest thing you can do, downsampling, for where's the best. But yeah, I didn't look at the difference between different implementations. But there are sophisticated models of upsampling, and they usually do worse than just a simple downsampling. And with downsampling, you reduce the size, so your training is gonna be faster as well, and you're gonna use less memory. So, but I guess if you want to tell your boss to buy more servers and that you have bigger data, then you just upsample everything. Yeah.
So let's say you have your model with parameters, and your model now in production, and this external event that changes their running training your data. How do you place another system which monitors your model? And if that actually changes dramatically, how do you update your model?
Yeah.
You have an alert that tells you if you fit the model.
Yeah. You kind of answered the question. I'm trying to find the slide. Yeah, you have all this here. So basically scoring, and then you have monitoring. So which is usually like a dashboard and then alerts. So yeah, you can look at, let's say you want to do fraud detection, then you can look at distribution scores or percentage of high scores within the last hour of the day and so forth, and then create alerts if those go up by something. And then you can look kind of manually debug what's going on. And some people are also doing like they monitor the inputs as well, so the distribution of the inputs. But you should at least, at minimum, monitor the distribution of the outputs. Yes.
So two questions. So talking about hyperparameter tuning, you mentioned boost, you mentioned your voice, but could you talk a little bit more about what your standard process is? I was kind of surprised you were using
Mm-hmm. Yeah. Yeah. Yes, this is for modern learning. So, so this is if you run the same model on, let's say, 1 core, 2 cores, because so all these three are kind of parallelized. So the way they parallelize it, because boosting is iterative, so you cannot learn the different trees parallel. So the parallelization is at each split actually. When you calculate it's called a histogram. That's what's parallelized. Trying to find out. All right. So basically, what you can do is just poke around, and with experience, you kind of try to find something, or so basically, why random search is better than grid search is that in random search, if you usually, so you might have like 10 hyperparameters, but really like 3 matter. And then if you take this Cartesian combination of everything with everything, then you're just wasting simulations or training on doing these grids on some variable that doesn't influence the output. So this is also called SGD, student gradient descent, that you give it to your students. I mean, yeah, there is something in this 2 blog posts, but it's so what I did here like a more extensive random search. So here I took the same data as in the benchmarks, and then I just did 100 iterations of random search. And in random search, you just specify the same, kind of like a grid, but it's not gonna do a Cartesian of all this. It's just gonna randomly poke on the space. And then this is done. So here, if you look at this repo, you would see kind of which are the top models, kind of what number of trees, what learning rate. So here are the parameters. And then this is basically the best model and the next ones. So yeah, you can see a lot of models here, and then a few really bad performance, and then here are the performance. And what you can also do is like take the top, because this might also depend on the data, on the test data. So what you can do is take the top 10 and assemble them in some way. Yeah, there are some papers about various Bayesian optimization models, but I never got into checking out if what they claim is true. There was some comment there was a blog post about this great is random search, and somebody commented that here's our paper, we are 100 times faster than random search, and for me it seems to be too good to be true. But I didn't really check the paper, but that paper is like 3-4 years old, so I think if it was really that good, people would win Kaggle with that, but I don't think it happened. So
On the random search, why don't you do like random, and then if it indicates like a space to search it, so do random in that space?
Yeah, you can do this kind of hierarchy. Yeah. So basically, you can do random, and then let's say it shows you that these are much better, and then kind of restrict and do random in this region. Yeah. It's more like an art than science. So there are kind of heuristics. Yeah, you guys have great questions. I think I gave. So this version of the talk is the first time here, but I gave older versions at various conferences, and yeah, I never got this many questions. So. So great audience.
Remember to eat some donuts before. No. And we have time. What time do we?